Hi students, so I am going to explain the definitions and terminology in module 3, which is number systems. From this module onwards, I'm going to discuss digital electronics part. The basic fundamental regarding to digital electronics is number system. So it is required to know some of the definitions and terminologies regarding to this module number systems. So first of all, define the number system. To represent any a number system can be weighted sum of some weighted factors. So if there are 4 types of number systems: binary number system, decimal number system, octal number system, hexadecimal number system. So the general definition of a number system is it is a system to represent a particular number, whether it is binary, decimal, octal or hexadecimal number. So by which we can represent a given number. So the basic, the very oftenly used the number system in our daily lives is decimal number system. Based on that also we can understood that what are the representation of all other number systems. If you see the decimal number system, 572. Basically, this 572 can be represented by number 5 in MSB digit number 5 is multiplied by the power of 10, like 10 power 3. So plus 7 is multiplied by power of 2, 10, like power of 10 square, and 2 is multiplied by this 10 power 0. So this is units place, this is 10th place, this is a 100 place. So totally we can call it as 500 plus 70 plus 2 into 10 power 0, 2. So that we can add these together, we call it as 572. Similarly, if you take any binary number 101, it is a binary number represented by base 2. This base 2, we can get that binary number. If you want to understood in a human language, this must be converted into decimal. So likewise, so there are these 4 different types of number system can be represented with the base radix. Like a number system base 2 is 2, and octal number system base is 8, and decimal number system base is 10, and hexadecimal number system base is 16. To understand in our language any number system, it must be converted to decimal number system, so that we understood that what is the exact value of that particular number. So how to convert these number systems and all we studied we have already studied. So the simple way is to represent that any number system from octal, from hexa, from binary. So we just use that multiple by base, multiple by 8, mul by 2, multiple by 10, multiple with 10, or any number like a 10 decimal to any number system, we use divide successive division method by 8, successive division method by 2, successive division method by 16, and hexa to binary, like binary to hexa to binary. So if binary to hexa, so take any binary number from left to right, left to right, take the 4 digit separate up, segregate that 4 digits each number, and then we can represent, is there any last bits, only 2 binary numbers, we can put zeros, so that for 2 zeros, so that total number of bits are make to 4, and then converted into decimal number, the hexadecimal number. 01004. It is 110 means 13 means like D, and this one is 2D 4 in hexadecimal number. So likewise, so divide into 4 bits. Binary to hexa divided into the binary numbers with divided with 3 bits each. Then you will get a binary to hexa. And if the number is hexa octal, that each digit represented with 3 binary numbers will get octal to binary. And that hexadecimal number, each digit represented with 4 binary number, you will get hexa to binary. And similarly, if you want to convert hexa to binary, there is no direct path by seeing these lines. So we never cross that lines. So directly we can't get that hexa to octal. So whether we will go to this path or we will go to this path or we will go to this path. So first finding the exact given hexa number converted to decimal, then converted to octal. Otherwise, that given hexa number first converted to binary, that binary number converted to octal. This way, the given number system, from given number system, you will find out any number system to any number system. Then we will see some more definitions, like gray code. What is gray code? Basically, gray code is an encoding of a given numbers, so that the adjacent numbers have a single digit difference. There are some procedure to convert of a given binary number to gray code. Once you got that gray code, if you observe that gray code, so the gray code basically after converting or after encoding that number, given number, we will get that the adjacent numbers have a single digit number difference by 1. So if you take any gray code of a given number, for example, binary number, this is binary number. So if you see this 10 0 0 1, this is binary number, and then take the MS bit as it is, and then the XOR operation of that one is 0 0 0 1. The XOR operation is 1. Sorry for that. This one 0 0 0 1 1 1 1 0 1 0 XOR operation, like take the 1 0. So the gray code of this one 0 0 0 1 1 0 1 1. The gray code of 0 0 is 0 0. Gray code of 0 1 is 0 1. Gray code of 1 0 is 1 1. And the gray code of 1 1 is 1 0. So here that MS bit is take as it is, and XOR operation of this one is like 1. So if you observe this number binary to gray, so in the gray code, so the sequence of this gray code 0 0 to 0 1 1 bit change, 1 0 1 to 1 1 1 bit change, 1 1 to 1 0 1 bit change. So the only single digit difference by 1. This kind of property that the gray code had, so that it will be referred as reflected code. And most probably this gray code, we use this gray code in a K-map to represent each minterm notation of the outside the box notation by this gray code only. And then XS3 code, so XS3 code nothing but whatever the given binary number is just add with just add with 3, then you will get a gray code, like XS3 code. If the given number is 0 1 1 1, what is the XS3 code for say this 0 1 1 is just put add 1, add 3, so that you will get 1 0 1 0. It is 10, it is 7. So when just add 3, you will get 10. So actually this 1010 for in XS3 is 7. So XS3 is also called XS3, and it is a non-weighted code, and it is a self-complementary binary coded decimal. So basically XS3 code is also called self-complementary code. What is self-complement code? Self-complement codes example XS3, 84, -2, -1, 24, 21. Such codes have the property that 9's complement of a decimal number is directly obtained by changing the ones like 1 to 0, 0 to 1. That property that self-complement codes had. So examples XS3 and 84, -2, -1. And define weighted and non-weighted codes. So if you weighted and non-weighted code basically is the how to define this weighted and non-weighted codes. Any code having a proper weights to represent that number, then that codes are called weighted codes. If you see the binary, or if you see that BCD code, so in the BCD code nothing but which follows 8421 code. What is the BCD for 8? 1000. What is the BCD code for 4? 0100. So this is nothing but each bit in these 4 digits, like 4 binary numbers. This one is power of 2 power 0, 2 power 1, 2 power 2, 2 power 3. This kind of weightage has been assigned to each digit, so that it will be called as weighted code. Non-weighted codes, for example, 1000 add with the XS3, so that this number is not non-weighted codes, because they don't have any weights of one after getting that XS3 of 8. So examples of XS3, 84, -2, -1 are also called non-weighted codes. What is standard and canonical form? Basically, if you take a Boolean function, a function represented in 3 variables, the order is ABC. If you represent any Boolean function on right side with the joining of one or more terms using AND operation and OR operation, if you the variables which I used, the literals which I used may be either in normal form or complemented form. For example, AB plus A bar B plus BC. This is a Boolean function. So this Boolean function, this is one term, this is another term, this is third term. These 3 terms are like combining together with the OR operation. So this A and B, the 2 variables are combining together, multiplied together with the AND operation. So here, this is called basically Boolean function. So now our question is, what is standard and canonical representation or canonical form of a Boolean function? Basically standard, canonical, this is basically canonical form. If you have a given any Boolean function, each term, sometimes we can also call as like it is a sum of product expression, Boolean function. All product terms are summed together. So it is a SOP form. In this SOP form, so each term is like a non-complete. So this is called basically canonical form. In any Boolean function, any one term is not having all variables, then the entire Boolean function is called canonical form. How can we convert this? Then what is standard form? Standard form is any Boolean function, each min term or max term in any Boolean function represented by all variables of a given function. Let us take this function is represented by 3 variables. So each and every term is represented with the 3 variables, then that Boolean function is called standard function. Then by the process of some techniques, like by adding some extra variables and then rearranging the equation, we will get the standard form. For example, this case, so here it is A, B, C is missing. We can add C plus C bar, because C plus C bar is nothing but 1 only. So A bar B, C plus C bar plus BC, A plus A bar. So we will get A, B, C by distributing distributing of that AB into inside the box. A B C bar, A bar B C plus A bar B C bar plus A B C plus A bar B C. So ABC is already repeated. We will take one time because A plus A, X plus X is equal to X in Boolean algebra. ABC, ABC bar, A bar BC, A bar BC also two times repeated. So we can take one time. So finally, we will take this one is 7. So we can also represent this one is in a sigma or M in terms. It is like 0 1 1 0 0 1 1 3 7. So this is nothing but standard form of a Boolean function. So each term having 3 variables. This is basically canonical standard form, and also there is some redundancy. So we have to reduce that redundancy. We will get final standard form ABC plus ABC bar plus A bar BC. Next, complements. Basically, in this model we have two complements: R's complement, R minus 1's complement. If you substitute R value with any base 2, 2's complement and 1's complement, 10's complement, and R minus 1, like R is equal to 1's complement, R is equal to 10, 9's complement. So the R's complement of n is defined as R small r power n minus capital N, and R minus 1's complement R small r power n minus 1 minus n. What does it mean? This R power n minus 1 means the maximum number of R's complement minus the given number. Then you will get the complement of that number. This is the definition, like some theorems or rules or axioms of a Boolean algebra. So in this, if you see the underform, 1 plus A is equal to A only, 0 plus A, any variable is equal to 0, A into A in Boolean algebra A, and A into A bar is equal to 0, and AB is equal to BA, which follows the commutative law. AB into C is equal to A into BC is a associative law. A plus BC nothing but this A is distributed with B and C, so A plus B and A plus C. So A is distributed to B and C. So absorption law, A into A plus B is equal to A only. And De Morgan's law, the product of complement is equal to complement of sum of individual complement. Similarly, R form just we got that dot become plus and plus become dot, 1 becomes 0, 0 become 1. The variables are unchanged. Then we will get that R form. These are all we get from this lecture notes from the IARE website and digital design by Marisma. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.